All right, so this is part 3 of Unit 3, and in this part, we are going to be looking at what are called matrices. And more than likely, this is a topic that you have not seen before, or you've only seen a very little bit of before. Now, this is kind of broken up into two parts here, and though the course technically covers a little bit deeper into matrices than what I'm actually going to cover, I would still want to expose you and show you to the topics that are covered in the course. So I am going to do some examples that are a little bit harder than what I would actually give you on an exam or a quiz or homework. So notice here, this next portion will not be on an exam, quiz, or homework, but I do want to show it to you so that if you see it in the future, you at least recognize it. And then you'll see at the bottom of the next page, the end of that portion where now you are responsible for this material. So here we have what is called, well, first we have a system of 3 equations here, and we have what's called an augmented matrix. And this is turning a system of equations into a matrix. So notice that we've just taken the coefficients of each term here, 3, 1, and 2, 3, 1, and 2, 1, 1, 2, 1, 1, 2, and 0, 1, 3, 0, 1, 3, and then the numbers on the end on the other side of this bar here. So this is changing a system of equations into what's called a matrix, and we can use what are called row operations to, rather than using the method we had before for solving this system, using row operations to solve this system. Now initially it's going to look like a lot more work than how we solved these in the last video, or in video 1, but as these systems get bigger, maybe we have 4 variables and 4 equations, or 5 variables and 5 equations. Using matrices becomes much more efficient. Now, what we're looking to do with this matrix is turn it into either row echelon form or reduced row echelon form. Row echelon form is turning it into where we have ones on the main diagonal, zeros below, numbers above, and then numbers over here. Reduced row echelon form is ones on the main diagonal, zeros below, zeros above, and numbers over here. And what this does is this tells me that x is equal to a, y is equal to b, and z is equal to c. So these row operations, kind of think of these as the rules that we have or the moves that we're allowed to do in this game. If you think of this kind of like a game or a puzzle, these are the things we are allowed to do. So there's really only 3 things we can do. We can switch 2 rows, so you can switch like a whole row, row 1 with row 2. The elements in any row can be multiplied by a non-zero number. So for example, I could multiply this whole row by -3 or something like that. And then 2 rows can be added together. Now, it doesn't get rid of a row if you add 2 rows together. For example, if I added row 3 to row 1, that's only changing row 1. Or if I added row 1 to row 2, then that's only changing row 2. So we're going to practice what all of those moves or all of those rules look like. This notation right here, row 1 is switching with row 2. That's all that means. That arrow right there, you could have an arrow just pointing that way, or you could put an arrow on the other end of it as well. And all of that means is that you're switching rows 1 and 2. So if we're using this matrix here, row 1 and row 2 are going to switch places. So this becomes 1, 2, -3, and 5. So row 2 moves up to row 1, and then row 1 is going to move to row 2. So 3, 18, -12, and 21. And then row 3 stayed exactly what it is. So it didn't move, didn't change, nothing like that. Right, so that is just switching 2 rows. Now the next operation shown here, we see this 1/3 in front of row 1. What that means is I'm going to multiply row 1 by 1/3. So this row 1 here, and unfortunately with this light here, it's kind of hard to see this. It says 1/3 row 1. Hopefully you can see that a little better now. And that's going to be just multiplying row 1 by 1/3. Well, 1/3 times 3 is 1. 1/3 times 18 is 6. 1/3 times -12 is -4. 1/3 times 21 is 7. and the rest of the rows didn't change, so those will just get copied down. All right, and then the last one, we can combine some of these. So here it says 2 times row 2 plus row 3. So I'm going to multiply row 2 times 2 and add that amount to row 3. So these steps are a little bit harder to keep track of. In this case, the only row changing is row 3. So I'm just going to copy down rows 1 and 2 right now. So 3, 18, negative 12, and 21. And 1, 2, negative 3, and 5. So 2 times row 2 plus row 3. 2 times 1 is 2, plus negative 2 is 0. 2 times 2 is 4, plus negative 3 is 1. 2 times negative 3 is negative 6. Negative 6 plus 4 is negative 2. 2 times 5 is 10. 10 plus 6 is 16. So that's what that kind of operation would look like. Now, what we're going to be doing in our next example is solving a system of equations using row operations. Now, when you first see me do this problem, it's probably going to feel like pretty overwhelming, feels like, wow, that's a lot to keep track of. Remember that you're not going to see this on a quiz or an exam or even homework. This is just me showing you an example so that if you ever see this in the future, you've at least seen one example before. So the first thing we're going to do is turn this system of equations into a matrix. Again, we're just taking the coefficients of all the x's, 3, 1, 1. Coefficients of all the y's, 1, 1, 3. Coefficients of all the z's, 2, 2, 2. And then all of these numbers on the end, 31, 19, 25. And now we're going to apply row operations to solve the system of equations. And I'm going to try and get it into reduced row echelon form. So what I want is to see this in the form where we have ones down the main diagonal, zeros above and below, and then numbers on the other side, and that'll tell me x equals a, y equals b, z equals c. So the way what we're going to do first is the first thing you want is to have a 1 right here. That's the first thing we want. So I'm just going to switch rows 1 and 2. Okay, let me fix that a little bit here. So rows 1 and 2 are switching. Row 3 is not moving, so I'm just going to go ahead and copy it down real quick. And row 1 is moving to below, so 3, 1, 2, 31, and then 1, 1, 2, 19. And then the next thing I'm going to do is try and get zeros right here. So I'm going to try and turn this into a 0 and this into a 0. And I can do that by multiplying row 1 by negative 3 and adding it to row 2. Go ahead and bring that over here. And row 1 is not going to change here, so I'm going to go ahead and just copy it down. And negative 3 times 1 is negative 3. Negative 3 plus 3 is 0. Negative 3 times 1 is negative 3. Negative 3 plus 1 is negative 2. Negative 3 times 2 is negative 6. Negative 6 plus 2 is negative 4. Negative 3 times 19 is negative 57. Negative 57 plus 31 is negative 26. And then in the next step, what we're going to do is I'm also going to multiply row 1 by negative 1 and add it to row 3. So negative 1 row 1 plus row 3. So negative 1 times 1 is negative 1, plus 1 is 0. Negative 1 times 1 is negative 1. Negative 1 plus 3 is 2. Negative 1 times 2 is negative 2. Negative 2 plus 2 is 0. And then negative 1 times 19 is negative 19, plus 25 is 6. Now, the next thing I'm going to do is just switch rows 2 and 3. And the reason I'm going to do that is because I want the middle row to be 0, 1, 0. And that's almost that. I have 0, 2, 0. And if I multiply row 2 by 1/2, then that will make that a 1. So I'm just switching rows 2 and row 3. Row 1 is not changing, so I'm just going to copy that down. And then this becomes 0, 2, 0, 6, and 0, -2, -4, -26. And then I want a 0 right here next. So I'm just going to add row 2 to row 3. So again, row 1 is not changing, just copying that down. Row 2 here, I'm also going to multiply by 1/2 after I do this. So 0 plus 0 is 0. Actually, we'll just leave that in another step. We'll do that separately. So I'll go ahead and copy down row 2. 2 plus -2 is 0. 0 plus -4 is -4. And then 6 plus -26 is -20. And then the next thing I'm going to do is try and turn this into a 1, and I'm going to try and turn this into a 1. So I'm going to go ahead and multiply 1/2 times row 2 and -1/4 times row 3. So from here, row 1 is not changing. 1, 1, 2, 19. And then I have 0, 1, 0, 3, 0, 0, 1, 5. So I already know z is equal to 5, y is equal to 3, and I can use these now to turn these into zeros. So I'm going to use row 2. I'm going to do negative row 2 plus row 1, and row 3 is not changing at all anymore. Neither is row 2. And -1 times 0 is 0. 0 plus 1 is still 1. -1 times 1 is -1. -1 plus 1 is 0. -1 times 0 is 0. 0 plus 2 is still 2. -1 times 3 is -3. -3 plus 19 is 16. And then our last step is going to be to turn this into a 0. I'm going to multiply row 3 by -2 and add it to row 1. This 0 is not going to change, or let me go ahead and first copy these down here. Your only row changing now is row 1. And this 0 is not going to change the 1. This 0 is not going to change the 0. -2 times 1 is -2. -2 plus 2 is 0. -2 times 5 is -10. -10 plus 16 is 6. And so this finishes out our matrix. Now it's in reduced row echelon form. 0 is above, 0 is below, 1's on the diagonal. X equals 6, Y equals 3, Z equals 5. Is our answer. Okay, so that's X, Y, and Z. So that is solving a system using matrices. Now again, you're not going to see that on a quiz or an exam, but it is helpful to just see how that works. The last thing that I'm going to show you that you will not see on a quiz or an exam is matrix multiplication. Now, this can only happen, you can only multiply two matrices if they have specific dimensions. So, m times n is the number of rows and the number of columns. The number of columns has to be equal to the number of rows in the second matrix in order to be able to multiply them, and then your answer will be equal to the dimensions on the outside, m by p. Now we're just going to look at multiplying 2 by 2 matrices, and this is the formula here for multiplying them. So if these are the matrices A, B, C, D, it'll be E, F, G, H. And rather than memorizing that, the easier way to do that is you're going across the rows, down the columns. So I'm going to show you how this will work here. Here, if we are multiplying these two matrices, we are going to multiply across the rows, down the columns. So this is the first row, first column, this spot right here. So first row, first column. 2 times -10 plus -8 times negative 9. So across the row, down the column. Okay. Then here we have the second row, first column. So second row, first column. 0 times negative 10. And then across the row, down the column, 4 times negative 9. Then over here, we're back in the first row, but now the second column. So first row, second column. So 2 times 1. And then going across the row, negative 8, down the column, times 17. And then here we have second row, second column. Second row, second column. 0 times 1. And then 4 times 17. And now we just have to simplify those. So negative 2 times 2 times negative 10 plus negative 8 times negative 9 gives me 52. And then 0 times negative 10 plus 4 times negative 9 gives me negative 36. 2 times 1 plus negative 8 times 17 is 134. And then 0 times 1 plus 4 times 17 is 68. And that is how you multiply 2 by 2 matrices. Now you can see here highlighted in blue, this is the end of the portion that you don't have to worry about seeing on a quiz or an exam. That means everything after this you do need to be aware of being on a quiz or an exam. Now what we're going to look at first are just basic operations with matrices. So if I have some matrix, let's just say we're talking about this matrix here, and we want to say what is the order. Well, the order of the matrix is just the dimensions, and you're always saying it is the number of rows by columns. Rows are horizontal, columns are vertical. So the number of rows is 2, the number of columns is 3. So the order of this matrix is a 2 by 3 matrix. Next, if we want to find a certain element in the matrix, here we want to find element 2, 3. So it's the second row, third column. So the second row, third column, that would be negative 1/5. If I want to find element 1, 2, that's not 12, but 1, 2, that would be the first row, second column, that would be 2. Now we can talk about matrices being equal if they have the exact same order and all the elements are the same and in the same place. We can also add and subtract matrices by making sure first that they have the exact same order or the same dimensions, and then adding the elements that are in the same location. So it's easiest to look at this with an example. Here I have 2 matrices that have the same dimensions. They're both 2 by 3 matrices. And I'm just going to subtract the elements that are in the same place. So this spot and this spot are the same location. So 0 minus negative 2 is positive 2. Negative 2 minus 7 is negative 9. 5 minus 3 is 2. 6 minus negative 9 is 15. 3 minus 5 is negative 2. And negative 8 minus 6 is negative 14. And that's it. That's subtracting matrices. Now we can have what's called the additive identity matrix. That means it's a matrix full of zeros that you can add and that won't change the value of it. Just like 5 plus 0 equals 5, it doesn't change its value. In the same way, if you add this matrix to any other matrix, it won't change its value. These are also some more rules. Basically, matrices work where you can switch the order of the addition and it gets you the same value. Even if you have 3, adding them in the different orders doesn't matter. Adding 0 gives you still the identity. If you add the opposite, so meaning a matrix with the opposite signs here, it equals the 0 matrix. And then you can do what's called scalar multiplication. You can multiply a matrix by a number. So we're going to practice some of those rules here. And we have an example here where it says find 2a minus 3b given that matrix A is this right here and matrix B is this right here. So the first thing I'm going to do is multiply matrix A by 2. So multiplying this matrix by 2, I get -2, 8, 6, and 0, minus multiplying matrix B by 3, I get 6, -9, 15, and -18. And then subtracting these, -2 minus 6 is -8, 6 minus 15 is -9, and then 8 minus -9 is 17, and then 0 minus -18 is 18. Okay. All right, one more example. If we have matrix equations, what we can do here, if I have the equation 2x plus a equals b, x is representing an unknown matrix that we're solving for. So that's what we want to find. So I could solve this equation first here. I could say, okay, 2x equals b minus a. So I just subtracted a over to the other side. And then rather than dividing by 2, what we're going to do is multiply by 1/2 on both sides. So that cancels out the 2 here, and x is equal to 1/2 times b minus a. So now what we need to do is with the matrix or matrices A and B, I need to find what this is. So x is equal to 1/2 times b, which is -6, 5, 9, 1, minus a, 1, 0, -5, 2, and x is equal to 1/2 times that. -6 minus 1 is -7, 5 minus -5 is 10, 9 minus 0 is 9, 1 minus 2 is -1. So from here, multiplying each of those elements by 1/2, -7 over 2, 9 over 2, 10 divided by 2 is 5, and -1 times 1/2 is -1/2. And that would be our answer. Now, the topic I'm really wanting you to get out of matrices is this next topic that we're going to go through, and this is called Cramer's rule. And this is another way for us to solve a system of equations. And of all of the ways I've showed you, using matrices, using the addition or substitution methods that we went over in videos 1 and 2, I think this is the method that takes the least amount of thought. Now, the first thing we need to look at is how to find what's called the determinant for a matrix. So if I have a matrix with elements A1, A2, B1, B2, the determinant is a number that is useful for the matrix. So we would find the determinant by multiplying A1 times B2 minus A2 minus B1. So multiplying down the main diagonal minus the opposite diagonal. And that gives me what's called the determinant. So what we're going to find is solving a system of equations using Cramer's rule. And what we're going to do is find the determinant for x using what we have here, and then the main determinant, and then dy over d. So I'm going to show you in the next example exactly what these are. It's easier to kind of go through with an example. So on the next page, we're going to do an example of using Cramer's rule for solving a system of equations. So here we have two equations, 5x minus 4y equals 2, and 6x minus 5y equals 1. And we're going to find three determinants. D, the main determinant, and that's just using these coefficients, 5, 6, -4, and -5. And then the x determinant, and what we do here is we're using the same numbers, -4, -5, but instead of the coefficients of x, we're going to use the numbers on the end. And then for y, we are going to use the same numbers as the main determinant, 5 and 6. And then the numbers on the end get replaced for the y coefficients, so 2, 1. And now we just need to find the determinants. So multiplying down the main diagonal, 5 times negative 5 is negative 25, minus the opposite diagonal, negative 4 times 6 is negative 24. A negative times a negative is a positive, so negative 25 plus 24 is negative 1. We're going to do the same thing for each of these determinants. 2 times negative 5 is negative 10, minus 1 times negative 4. And then 5 times 1 is 5, minus 2 times 6 is 12. So negative 10 plus 4 is negative 6, and 5 minus 12 is negative 7. Then going ahead, and our x value is equal to dx over d. Our y value is equal to dy over d. So in this case, that would be negative 6 over negative 1 and negative 7 over negative 1, which gives me 6, 7. And that's our solution. So I like this method because it doesn't take a lot of thought. All of the math you're doing is just multiplying numbers. There's a lot less, or really there's no algebra in this method, and I think it's the easiest to think through once you get the method down. Now we can also use this method for 3x3 systems. So like what we did in videos or in parts 1 and 2 of Unit 3, we solved 3x3 systems of equations, like what you're seeing here. We can also do that for 3x3 systems. We can use Cramer's rule. Now let's first look at finding the determinant for a 3x3 matrix because it's a little bit more work. This is the formula for finding the determinant of a 3x3 matrix, and if you had to memorize that, that would feel overwhelming. But I have a trick for memorizing it. If you have a determinant here and you copy these rows next to it, what you're going to be doing is multiplying down these 3 main diagonals. So A1 times B2 times C3. So A1, B2, C3 plus B1, C2, A3 plus C1, A2, B3. And then you're subtracting up the opposite diagonals. So minus A3, B2, C1 minus B3, C2, A1 minus C3, A2, B1. Okay, so that way you're not memorizing anything, you're just subtracting down or adding down the main diagonals and subtracting up the opposite. So we're going to do that in this next example here. It says evaluate the determinant for the following matrix. So the first thing I'm going to do is just copy these numbers next to it. And then we're going to go ahead and multiply down that main diagonal. So 4 times 3 times 1 is 12. And let me go ahead and actually just write it out. 4 times 3 times 1 plus 1 times 4 times negative 3 plus 0 times negative 9 times 8. And then we're going to go up the opposite diagonal, minus negative 3 times 3 times 0, and then minus 8 times 4 times 4, and then minus 1 times negative 9 times 1. So let's actually calculate out all of those. 4 times 3 times 1 is 12 plus negative 12. And then 0 times anything is 0. And then here we have 0 times that, so that's plus 0 again. And then 4 times 4 is 16, times 8 is 128. So minus 128. And then a negative times a negative is a positive. 9 times 1 is 9. So the 12 and the negative 12 cancel out here, and I have negative 128 plus 9, which gives me negative 119. Okay. So the calculations here, I did it all, by hand, but you can do a lot of these calculations in your calculator. So using Kramer's rule for a 3 by 3 matrix, the x value is still dx over d, y is still dy over d, z is still dz over d, but now d is that main determinant, the coefficients of x, y, and z. dx is replacing the x's with the numbers on the end, and then y's and z coefficients. dy is x staying there, z staying there, but the y's are replaced with the d's on the end. And then z is x, y coefficients, and then the z coefficients are being replaced with the d on the end. So we're going to do one of these examples, and then that'll be the end of this video. So here we have Kramer's rule, and then we're going to do this example right here. So we have a 3 by 3 system, and we are going to use Kramer's rule. So let me go ahead and set all of these up first. So I'm not going to talk through a lot of this. It's really just writing these determinants. So the main determinant is the coefficients of x, y, and z. And I shouldn't have written that last part. It's just the x, y's, and z's. dx is replacing the x's with those numbers on the end, -4, -6, and 3. And then it's 2, 4, 3, -1, -2, 1. dy, x's stay the same, 1, 1, 2. Z's stay the same, -1, -2, 1. But y's get changed to the numbers on the end, -4, -6, 3. And then dz, x's stay the same, so 1s and 2, 4, 3. But then the z values get changed to, again, the numbers on the end, so -4, -6, 3. And now it's just evaluating all of these determinants. Let me zoom out a tad here so hopefully you can see all of them. So I'm going to first copy these rows down on the end, and then I'll go through and evaluate all of them. So 2, 4, 3, -4, -6. And I like setting all of them up first, and then just going through and evaluating all of them. So, evaluating the first one here, 1 times 4 times 1 is 4. 2 times -2 times 2 is -8. 1 times 1 times 3 is -3. And then the opposite diagonals we subtract. So 2 times 4 is 8 times -1 is -8. And then here we have -3 times 2 is -6 times 1 is -6. And then 1 times 1 times 1 times 2 is -2. And then I'll go ahead and evaluate all of them at the end. So again, down the main diagonal, -4 times 4 is -16. And then we have -12, and then plus 18, minus the opposite diagonals. 3 times 4 times -1 is -12. And then we have 8 and 3 is 24, minus 24. And then minus -12. Okay. And then the next one, -6 plus 16 minus 3. And then here, minus 12 minus -6 minus -4. Then we can total that. And then for the last one, down those main diagonals, we have 12 and then minus 24 and minus 12, minus opposite diagonals. 16 times 2 is 32, so minus negative 32. And then minus negative 18. And then minus 6. All right, so now we can go ahead and use our calculator, or you can add them in your head, whichever you prefer, and you can go ahead and actually calculate all of these. So you might pause the video and go ahead and actually just calculate all of these on your calculator to make sure that you're knowing how to, actually type it into your calculator, calculate all of these things. But when you add all of these up, you get 5, negative 10, 5, and 20. And so using those numbers here, finding our x value, x is equal to dx over d, y is equal to dy over d, and z is equal to dz over d. And dx is negative 10, d is 5, dy is 5 over 5, and then 20 over 5. So 4, 1, negative 2. And that is our answer. All right, and so that is the end of Unit 3, Part 3.